Hello, welcome to our ME106 project presentation. My name is Yuhao, and I am joined by my teammates Victor, Drake, and Miguel. And today we will be showcasing our automated insect defense system. We wanted to create an automated system that could help shoot down insects while reducing human interaction and still remain safe for indoor and outdoor use. Our objective was to design a Raspberry Pi Pico-based turret system capable of automatically detecting insect movement using IR sensors. The system uses a pan and tilt mechanism to scan the environment while connected to a water pump to shoot water at the insects. A light sensor is also used to detect dark conditions and activate an LED light source to attract bugs during the night. And to keep the project affordable, we purchased and borrowed low-cost electronics and 3D printed our components.
Let us now get into the mechanical design behind our turret. First, a quick overview of the turret. Since we are utilizing two micro servo motors, we went for a small and simple design. This picture shows the turret fully assembled from 4 pieces, which we'll refer to as the bottom base, upper base, rear of the turret, and the front of the turret. The bottom square base simply has a small container which is used to hold a servo motor in place. Instead of using gears, we decided to mount the upper circular base directly on the servo motor shaft. This base contains 2 towers. One holds the other servo motor, while the other has a circular opening used for a cylindrical joint. The rear of the turret will be connected to a PVC tubing where the water will be pumped into. It also contains a border that will help in placing the front piece of the turret. The front of the turret is glued into the previous piece we mentioned. This has latches that are used to hold the infrared sensors in place. Some challenges we faced. Since we did not consider the wiring of the servo motor, it did not fit into the container. Instead of modifying the CAD design and the 3D printing again, we decided to use soldering iron to open a small gap for the wiring to go through. Also, since we didn't use gears, there was a slack where the shaft of the servo motors were inserted. This made the movement very sluggish. To combat this, we tried to incorporate a straight double-ended servo horns, which improve its movement. Lastly, we tried to print the turret in one piece, which presented printing problems when it came to the hole for the water. To solve this problem, we decided to split the turret into two pieces, which worked perfectly fine.
Object, the actuator we chose to use was a water pump, a submersible 3-volt DC water pump. We decided to use it at 5 volts instead, though, to try and increase the power of the pump. The current was 200 milliamps with a flow rate of 100 liters per minute. To communicate the pump with our Pico, we used a motor driver, the DRV8833 DC motor driver. It has an H-bridge integrated inside of it, uses the same logic as the Pico, being true or false. It has a built-in kickback dial to protect from current spikes, and it limits current to 1 amp. For the wiring, the pump was connected to the motor driver through A-out1 and A-out2. We used the power supply of the lab at 5 volts to connect to the motor driver, and the ground of the power supply was also connected to the motor driver. AN1 was connected to GP17, AN2 was connected to GP16, and SLP was connected to GP27 on the Pico.
So, regarding our insect attracting light, we decided to use a simple light detection system. For our light sensor, I decided to go with the VML 7700 ambient light sensor to detect surrounding light levels and lux. The sensor itself is fairly small, as highlighted by the picture on the right, and it communicates with the Pico and reads the light level while comparing it to a light threshold. So when the environment becomes dark, the Pico automatically activates the connected LED. And for the bug attraction light, we are using a simple 5mm white LED. It operates at around 3 volts and draws approximately 20 milliamps of current. For connections, the light sensor is connected to the Pico using I2C communication through the SDA and SCL pins on GP4 and GP5 respectively. The sensor continuously measures ambient light levels and sends the lux data to the Pico. The LED is connected to the GP20 pin along with the 200 ohm resistor to limit current and protect the circuit. When the detected light level falls below the program threshold, the Pico automatically turns the LED on. And for integration, the LED light is attached to the head of the turret, and as long as it is exposed, the sensor can be located anywhere in the system.
Alright, and now for the last part of the presentation, we're going to be talking about the IR sensors, which are acting as the eyes of the turret, and how they can communicate with the servo motors to move our turret around and point where it needs to be pointed at. Now, the IR sensors themselves are pretty basic. They run on a logic of saying, do I see a target in front of me, yes or no? The range of its detection is about 30 centimeters, and it runs at 3.3 volts, meaning that it can be run fairly comfortably on our Pico. These sensors are also very cheap, meaning that we can grab a lot of them to be used on our Pico without worries of financial. Some of the challenges that come with these sensors, though, is that they can be unreliable at times, especially when it comes to the color of an object. Lighter colored objects can be detected much further, while darker colored objects needs to be much closer to be detected. And if the object is black, it's just not going to be detected at all. And these will be communicating with our servo motors to point our turret. Now, these are the SJ90 servo motors. They are given out by our lab. They're fairly cheap, and they are small, meaning that they won't be adding too much weight to our project, which is very needed. They all ran at 5 volts, which should have meant that we could run it on our Pico board, but they drew too much current when we were using 2 motors, so we needed to use an external power supply instead to power them. these motors are also fairly weak, and that made us have to design our parts to be much smaller and much less massive in order to make sure that the motors have enough torque to point them. Here's a basic circuit diagram that we have. We can see that there are IR sensors, and the light sensor here are connected by the 3.3 volts with our Pico, while our servo motors and the pump is powered by the power supply at 5 volts. Here's a basic overview of the code's flowchart. Once the turret is on, its basic behavior is to scan the room, meaning that it's going to be moving left to right. If the room is dark, then the LED should turn on. If not, then the LED will stay off. And then it asks itself, do my sensors see a target in front of it? And if the answer is yes, then it has to ask itself, do all the sensors see a target? If it does, then it will fire water at the target. If not, then where it will need to turn based on which sensor sees the target. For example, if it was the right sensor, it will turn right. And then we keep going through that loop until it either sees that all of the sensors see a target, or there's no target, meaning that it will go back to scan the room. To end the presentation, we'll have a short video of our turret working in the lab.